Okay, so we start with the idea of alternating currents. Okay, the formula for this doesn't really matter at this point, but if it's a result of a coil rotating in a magnetic field, then it would be a sine wave. Okay, and that's your official alternating current. Um, Now, what we're really trying to get at is the whole idea of back EMF, which you should be familiar with. If you change, well, we'll see. Okay, so the current results in a magnetic field within this loop. Now, this just depicts the source, some resistance, and a loop almost closed, but not completely closed, a loop of area A. Okay, now we can assume a circular loop, but it doesn't necessarily have to be circular, it could be square. The current, as we know now, results in a magnetic field within this loop. Now, as the current changes, which it continuously does, with alternating current, what's going to happen in the loop? Well, I posed the question, I got the answer. The magnetic field is going to change. And of course, it answered it. It also says proportional to the current. Okay? That's mostly true, especially if the current's changing slowly. But you've got this back EMF. Okay. Okay, so as the current changes, magnetic field in the loop changes. Say creating its own EMF. Which is changing. Okay, that EMF is changing, and I should say creating its own changing EMF. And since that is changing, it creates its own EMF, and that EMF is opposing the change in current. So it slows down the change in current. Okay, which is why it's not quite correct. In some cases, it'd be really incorrect, depending on the inductance of that loop, which is just the amount of back EMF you get per unit of rate of change of current. And that's a mouthful. Hopefully you understand things well enough to understand that. Okay, so, and I can write that out. Inductance of the coil it's the induced EMF per unit of rate of change of current. Definition is EMF is L. L is the symbol that's often used for inductance, times the rate of change of current. And it would be negative. Because it's a back EMF. If your current is decreasing, it tends to fight the decreasing current with an EMF in the opposite direction. Okay, now it would be difficult to figure out what the inductance of a single loop is. Simply because we can calculate the magnetic field at the center if we know what the current is. Okay. But we don't know what the magnetic field is at other points. Now we could figure out the magnetic field at any point, but there wouldn't be any symmetry. So our integral would be either tricky or impossible. Okay, take my word for that. Just go ahead and try it. Okay, try figuring out what the magnetic field is at a point, say halfway between the center and the loop. Okay, there's a certain amount of symmetry in that, but there's a certain amount of symmetry in any level. Calculate. Your integral is going to be nasty. Okay, perhaps even impossible. Okay, now if you have a solenoid, lots and lots of coils so that you have almost a uniform field within the loop, then you can kind of figure out the inductance. Okay, if you have a set of Helmholtz coils, you can come close figuring out the inductance, although the magnetic field between the loops is not totally uniform. Okay, so inductance can be predicted fairly well. Solenoid since the magnetic field is pretty uniform, psi, Ampere's law, with a couple of symmetry arguments and so forth, ensures that. For just about anything else, say for just about any other configuration, not so much. You just got to measure it. Okay, I'm sticking my neck out when I say for just about any other configuration, because I haven't tried to engineer other configurations. Okay, and engineers probably have, and research physicists, and so forth. Okay. So there could be something, it probably is, there's probably much that I'm not thinking of. But I'm just going to say that we don't try to figure it out for anything but a solve. And I think it'd be fair for you. So maybe a set of Helmholtz coils with an iron core come close. Set of Helmholtz coils comes fairly close. In some ways, it's kind of close to solenoid. You try to apply Ampere's law. the Helmholtz coils and see what comes out of it. Um, so I'll just say most configurations you got to measure. All right, now we're going to postulate a source with a resistor and an inductor with inductance L. Okay. Source can be changed. Maybe it's a plain old AC source, maybe it's a square wave, maybe it's a triangular wave or a sawtooth or whatever. Okay. All those configurations are configurations that you've seen since you've had a differential equation. Learned how to analyze those things, including with Laplace transforms. Okay. You probably don't remember. If you had to do it, it would come back to you. And hopefully it will come back to you when you have to do it. You're not going to actually have to do it for this course, but I'm still going to kind of refer to the differential equations when we get to the tough ones, okay? Like, for the sawtooth, square wave and all that stuff. For a simple alternating current, we can do it using calculus one, okay? So we try to trace the EMF of a loop goes around like this. And if it's an alternating current, of course, sometimes it goes this way and sometimes it goes this way. Okay. Matter of fact, let's just assume the standard, which is a counterclockwise loop, positive direct. Okay. The source is going to be minus the EMF of the source. Okay. Just like when you go across a battery, you go from negative to positive, then you're going to have voltage drops across the resistors. And the voltage drop across the source is the negative voltage drop because it's a voltage rise. Okay, we've talked about that and you should be kind of used to that. The resistor, it's the resistance times your current as a function of time, right? Across the inductor, well, di dt. Conservation of energy tells you that the work done around the loop is zero. Work around a complete loop is zero. And that's really a statement of conservation of energy. And this gives you the equation L di dt plus Ri minus your EMF is zero. So that have this equation. It may be second thought. Makes sense? Okay, well, your homogeneous equation L di dt plus Ri equals 0, which becomes let's think of clearly. If you put the Ri over on this side, L over here, you can quickly rearrange it. It's a separable equation. Details of that. Don't remember how to do a separable equation, review it. As it's done in calculus 1. You certainly did it. And differential equations, of course, you get the natural log of the absolute value of I equals negative R over L plus an integration constant. This leads to magnitude of the current being e raised to the c power times e to the negative R over L times t. Since the exponential function is inverse of the natural log function, and if that doesn't seem familiar to you, you want to really think about it. So that's calculus 1. Okay. So there's your solution. That's I as a function of t. Okay. Where A is plus or minus e to the c. Note that this is the absolute value of I, so I would be plus or minus what you have over here. If e to the c is a, and e to the c, of course, is always positive because your exponential function never negative. No negative power of e, it's going to go negative. Okay, it's just going to get really small. Okay. You have this function where a equals plus or minus e. So why don't we just write it? Instead of a, let's call it I naught. Okay, whatever say your t equals 0 current is, well, that would be the meaning of a. So again, thoroughly understand all of this. If you don't, I'll be sure by the time you come in here next time to do. Because we're gonna start in lab very possibly by trying to observe this. Okay. Now this corresponds to the case where your source is zero, because it's homogeneous case. Okay. But somehow you've got a current in the loop. Perhaps that current in the loop could be induced by a magnetic field. Okay. Which would be kind of complicated because then you have a back EMF of a back EMF. And, you know, but something to deal with. We just don't go to the bottom in this course. Okay. Unless I decide to put a really perverse problem in the exam. And usually I got at least one of those. So you never know what you're going to see. I usually don't count it unless you get one. So one of those. All right. Wouldn't expect you to necessarily think it through at that level, but I hope. All right. What does a graph of current versus time look like? Source EMF is zero. But one way or another, you've got a current in this configuration. Perhaps what you've done is you've inserted a capacitor in there. Well, a capacitor complicates things a whole lot. Okay. We'll talk about what happens if there's a capacitor. We might go ahead and talk about that. We'll see. Okay. But we got the current EMF source is zero. So you've got I equals I naught here. What's the graph going to look like? Can you sketch me a picture? What the graph has to look like? Okay, well, now negative exponential looks like this. It approaches zero asymptotically. E, the negative, increasing negative power is like 1 over E. The positive power, E, grows very rapidly. Positive power, increasing positive powers, so the reciprocal drops off very rapidly. Now, the problem we're going to have trying to observe this in lab, and it's fairly easy to observe, a parallel combination of just a battery. Doesn't even have to be an AC source to get an initial current in here, and a switch where we just cut it off. We can set the interface to trigger when the current starts to change. Okay. And then we get to observe this and compare it with what we get theoretically from our inductor. Okay. Fair enough. Okay. Well, we've been able to do this every time we try. So I don't think we'll have any trouble. It's just that for any reasonable resistance, and you don't want too much resistance or you don't get much current, and it's hard to observe, right? For any reasonable resistance, it gives us current we can actually observe and actually measure details of the curve. It happens really fast. Millisecond or less. Fortunately, our interfaces allow us to manipulate that. So you got to get to manipulate that and see if you can just observe this. Okay. Now, what's the half-life? No, you have a half-life because exponential functions either have doubling times or half-lives. Okay? The half-life occurs when this factor here is 1/2. Because if this factor is 1/2, you're going to get half of I naught. Okay? And if you have a different t, well, it's easy to get there too. I'm not going to go through the arithmetic of it. It's pretty obvious. Okay? But we get e to the negative r over LT equals 1/2. How do we solve this? Can you tell me, as soon as I pause the video, how we solve this? I got an interesting answer. Due to my moderate hearing loss and uh, maybe the enunciation of the person that said it, I heard by prolonging the exponential function. And I was actually a little worried because that came from somebody I'd have expected a good answer from. But he said natural logging, okay? In other words, taking the natural log of both sides of the equation, and yes. And that answer was good. I just didn't hear it. Did you hear it?
Yeah.
You heard what he said?
Never heard that.
You didn't understand what he said? It's on you. Okay.
Okay.
Use good enunciation when you're trying to communicate with other people who might just, plug in the wrong nuclear code and blow up the world. You want to be very careful with your enunciation. Okay. I'm not always either, so okay, we take the natural log of both sides. We don't go natural logging both sides, although that does make sense if it's in a plural. Okay, so we do the natural log of e negative Earl t equals the natural log of 1/2. Natural log of 1/2, I think, is 0.69 something. It's real close to 0.7. So I'm just going to ballpark 0.7. And I'm going to get negative r over LT approximately equals 0.7. So the t approximately equals, and that would be negative 0.7. That's 0.7 times r over L. Okay. Now you're engineers. Okay. You want some numbers. Okay, now you see, I talk about enunciation and stuff. I looked at the inductor we have on this circuit board here, and it's 8.2 millihenries, 0.0082 henries. It's actually fairly high inductance for small coil. Okay. Of course, I put that in here, that's small, with any resistance, that gives us really long time. That is counterintuitive. A big inductance is going to slow things down. A small inductance is going to allow things to happen fast, right? Because I just wrote R over L because I love to say Earl. But it's L over R, obviously, if we solve the equation carefully. Okay, so unit of inductance. Well, L di dt must have units of volts, right? Because L di dt is the back EMF. EMF is in volts. Okay. The SI unit of dIdt is amps per second. So the volt second per amp, which is like a joule per amp coulomb times second, which is a lot of other things. A joule is what? Kilogram meter per second squared. So you get a second in the denominator. You can arrange the units any way you darn well please. Let's call this unit Henry. It's the Henry, Henry being the guy that studied this stuff and got his name put on the unit. Okay. Experimented with it. Did some interesting things. I don't remember what. I didn't spend a lot of time in his lab. I talked to him a few times. It was 200 years ago, whatever. Okay. So that's what a Henry is. It's what you multiply by dIdt to get volts. So I'm taking a little poetic license. L in Henry's times the dIdt is going to give you volts. And now all the units work out. So tell me, what are the units of L over R that come out seconds? L over R should be seconds. So just taking volt seconds per amp. Divided by, what's the unit of resistance? Well, it's current times resistance, which is the most common way to use it, but it ranges in various ways. Just avoid confusion. Resistance is voltage over current. Okay. So that this will be second per amp over volt per amp. Well, that works out rather nicely, doesn't it? Now we could reduce these two units to SI units. You know, volt is a joule per coulomb, right? It's kilogram meter per second squared per coulomb. Okay. You take one of those second squareds and, well, you have to write it out to make sense of it, and also we're going to say it right. Okay. But it turns out you can express it in terms of fundamental units, which are amps and kilograms and meters seconds. Okay. And you could write out the lassitude of this and work out what this is, and it would still all rearrange to give you seconds. Okay, so when we look at this equation, we know we have henries times amps per second. All right. Well, the other thing is that's your half-life. Okay, so okay, so you got 10 ohms, 10 to the negative second henries, then what's your half-life? Just label this half-life T, so half. Okay. And it's 0.7 L over R. Point seven times 10 to the negative second henries over 10 ohms. Well, 10 ohms is 10 volts per amp. A henry is a volt per amp times a second, so you're going to get a second. That one doesn't seem particularly good. So if you change ohm to volts per amp, henries as volts seconds per amp, you're going to get seconds. That's 0.7 milliseconds. So it happens in a hundredth of an eye blink. So we have options for how to use our instrumentation. We can set the thing to trigger, okay? Or we can just do an observation for like a second and then zoom in on it until we see something. Okay? But of course, in order to get a nice smooth curve, we're going to have to take maybe 100 observations in about a millisecond. That's 100,000 observations per second. And if we do that for a second, that thing's going to be cranking for a while. Okay, I think it'll do it. I think that's getting close to its capacity. Maybe it's a little beyond its capacity. So we have all kinds of things that we have to think about. We have to understand this relationship before we can reasonably do this lab. Okay, and that's the first thing we want to do is be able to observe this. Now I'm going to digress about what happens if we got the capacitor and a resistor in the circuit. Turns out the mathematics is identical to the mathematics that we get here. Okay. Um, an RC circuit has a capacitor with resistor and source. Okay. Capacitor, resistor, source. your voltage drops. Says what the sources are. Okay, you have a negative voltage drop across your source. Q over C. Resistor. It's IR. So some of the voltage drops is zero. So we could write Q over C plus IR minus your EMF, zero. At that minus EMF, we add to both sides and we get this. Well, what's your current? Your current's the rate at which you're pulling charge off of one plate of the capacitor and putting it in the other. In other words, your current is the rate of change of the charge on the capacitor. The homogeneous equation is R dq dt plus Q over C equals zero, which rearranges to dq over Q equals RC dt. Oh, you know, when I solved this equation over here, it's a terrible oversight. And we rearrange this as a separate, when we separate the variables, we get a di dt over here and a negative R over L times I over here. And we definitely have a dt here and an I here. I didn't write out the dt, but I integrated it as if it was. So I didn't write the dt, just kind of lumped oversight to make sure that we have it right there. Now here, when I did write the dt, and when I did, I realized, whoa, wait, I don't think I wrote the dt. So separating the equation, we get dq over RC. And it'll be negative here. It'll be negative 1 over RC. I don't know what to do. But it's dq over q here. And you divide through by the RC, you get a q over RC. I got all the steps. So, excuse me. Make sure we understand all the steps. Okay. So we could write that as dq dt plus q over RC equals 0, divided through by R. So we could write dq dt equals negative q over RC. So that dq over q equals negative 1 over RC dt. Okay, that's what I get for skipping steps. Okay, articulate. Okay, so we get this, and we integrate both sides, and we get the natural log of the absolute value of q equals negative t over RC plus a constant. So the q equals q dots here, because we kind of do it over there, q naught e to the negative t over RC. And the details here to here. Just take the natural log of both sides. Just exponentiate both sides. E to the c becomes your coefficient. Since you have absolute value of q, it's going to be plus or minus e to the c, and q naught then. This. And you recognize that this equation is identical to that equation, except for the constants in the names of the terms. Then, of course, if we want to get the current, we just take the derivative with respect to time, and that's very straightforward. Chain will give us a negative 1 over RC here times q naught, and then you still have your e to the negative t over RC. Also, it's still on the board here. It's approximately 0.7 over RC. Now, on our circuit board, I have other devices around wherever I put the circuit board. Over there, yeah, I'll put it back there. Okay. It looks like we've got capacitors on the range of 100 microfarads. I think all we've got is 100 and 330 microfarads are just two capacitors, but that's enough to play around with. Capacitor is 100 microfarads, and the resistance is, let's say, 10 ohms. I think what we got is 10, 33, and 100 ohms. Kind of a geometric sequence. 33 is about the geometric mean, 10 and 100. Got this and this now. say, right, let me stop and think. Don't even ask. But it's not 0.7 over RC, 0.7 RC. Again, I did that too fast. If I set this, if I set e to the negative t over RC equal to 1/2, then negative t over RC is equal to about 0.7. So that t would be 0.7 times RC. So if you write it out, it's analogous to what I wrote here. Okay. 7 would be 1 over RC times 2 equals 0.7. Anyhow, it's very close to 0.7 RC, which is 0.7. Now, what's a farad? It's a volt per coulomb. Okay. That coulomb volt, sorry. And you got to manipulate the units a little bit. Ohms is, again, volts over amps. And you put it all together and you find that RC has units of seconds, units of time. In this case, you got 10 times 100, which is 1,000, but it's microfarads, which is billionths. And you put all that together. Wait a minute, got 1,000, yeah. 7/10 of a microsecond again. Okay, which turns out to be identical to what you get with that inductor and 10 ohm resistor. Okay. You should work out the units of this, make sure you understand it. Okay. What's capacitance? It's power over voltage, right? Coulombs over volts. So that's in microcoulombs over volts. This is in volts per amp. And units work out. So just work them out. You see then that with the circuit board we're provided with, we're going to have to be measuring things that happen in the millisecond time frame, in frame of maybe up to a few milliseconds. Okay. Now we could go to 100 ohms, and that would give us 0.007. That gives us 7 milliseconds. That's like an eternity. Okay. We could put another resistor. We put a length of nichrome in the circuit. Okay. I'd have to have quite a bit of the nichrome that we have to make 100 ohms, but we've got resistors. We put 1,000,000 ohms in there and see what the half-life is. Well, that would be in several minutes, maybe in the order of hours. Okay. Put a megohm in there. That's going to be 100,000 of these, 10 to the 5th of these. It's going to be about 70 seconds. Possible to do that, but we get a pretty small current and it might be difficult to measure. Of course, we could measure voltage. Take the voltmeter, pull off enough current, mess this up. I don't know. It'll be interesting to see. We'll play around with it and just see what we get. You understand? You're going to get things to play with. Okay. I've digressed from the essence of the upcoming chapter to stuff that we're actually going to be looking at, because I'm going to put a little more emphasis on AC circuits. And on the actual mechanism of induction, because it's not hard to understand the basic mechanism of induction, right? I'll assign a few problems. See just what I end up assigning. I'll do that this afternoon. Okay. And we'll see how it articulates with the next couple of chapters in terms of what I think you're understanding right now. Be sure you understand these equations. Also, how do you solve the non-homogeneous equation? Okay. I'm not going to require that you do that because that's a differential equations topic. But it's pretty easy. You just, if this is a sine function, then I is going to be a sine function. And you just use undetermined coefficients, basically. Okay. You don't have to use variation of parameters or any of that stuff. Undetermined coefficients are pretty easy. Okay. You're going to get a combination. Okay. If I is, let's say, cosine function, then di dt is a sine function. So you got a sine function plus a cosine function. And if this is a cosine function, then you know the argument of sine functions. The argument of cosine functions and other, and the equations are really simple. That's one of the easier things in a differential equation. As long as it's not accompanied by say an LRC circuit with some confounding factors, okay? In these cases, it's easy, and I'll probably do it next time just to show you how nicely it works out, because it'll be handy for analyzing the lab. It's kind of optional, but it's probably something that I'll put on the test as an optional question. And you should be well equipped to do it. And if you aren't, no prejudice, because I can't officially make that part of the course.